Hi folks, and welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to use partial fraction decomposition to evaluate integrals. So what we're looking at here, this is problem number 30 in the current textbook I'm using. We're going to look at the integral x squared plus x over x to the fourth minus 3x squared minus 4 dx, and try to evaluate the antiderivative of that function. Now, I've already done step one here. I've factored that denominator. Hopefully I factored it correctly. I tried to get my second cup of coffee in before class here, but I believe that denominator will factor into x squared minus 4 times the quantity x squared plus 1. Now, x squared minus 4 can be factored further, so I'm going to write one more line here. I'm going to write this integral x squared plus x over x minus 2 times x plus 2 times x squared plus 1. Okay. Oops, dx. Darn it. So now the idea is to take this and write it as the sum of a bunch of smaller looking fractions. So I'm going to take this. I'm going to kind of cheat here. And as we look at this, the first important step is realizing, the different types of fractions that we may have when these are added together. One of the possible fractions has a denominator of x minus 2. Since this is a linear factor, all we need is a constant up above it. Another possible denominator is the x plus 2. Again, because this is linear, we're looking for just a constant above that. Third possible denominator is this animal, this x squared plus 1. Recognizing this is a quadratic, it cannot be reduced further, this could potentially have a linear term up top. So I'm going to put a cx plus d on the top of this thing. Right. Now the idea here is to try to find a, b, c, and d so that we can take this big mess and write it as the sum of some smaller messes and then integrate the smaller messes independently. Now, as far as finding these constants, now we just make use of basically how fractions add. These all have to have a common denominator here when they add them, and this product right here is the common denominator. So, and what I'm going to do, let's see, is I'm just going to give this a name here and call that like z, because I don't feel like rewriting that thing over and over and over. In order to turn this into this fraction needs to be multiplied by x plus 2 times x squared plus 1. So in the top of this, we're going to have a times x plus 2 times x squared plus 1. And again, that's all over the denominator I'm calling z. I just don't want to rewrite that over and over and over. Our second fraction here needs to be multiplied by x minus 2 times x squared plus 1 over x minus 2 times x squared plus 1. So that's going to give us a b times x minus 2 times x squared plus 1. Our third fraction here, the denominator is missing the x minus 2 and the x plus 2, so you would have to multiply this fraction by x minus 2 times x plus 2 over x minus 2 times x plus 2. If we do that, that's going to give us cx plus d times x minus 2 times x plus 2. So there's the first very, very important line of this problem. I'm going to go ahead and write another line here. X squared plus x over, now at this point the actual denominator doesn't even matter. I'm just going to put over z equals, and I'm going to go ahead and expand this out. So when we multiply this out, we're going to get x cubed for the first product plus x plus 2x squared plus 2. And again, that's all over z. Plus, next term, we're going to have b times Okay, this product is going to give us x cubed. Then the outer product is going to be plus x. Inner product is minus 2x squared. Last product is minus 2. And again, that's all over z. Next term. And I'm not going to multiply this all out quite yet because I don't have the room. So I'm just going to leave this cx plus d times x squared minus 4. And again, that's all over z. Now, this is the really important line. The denominators do not matter. In fact, they can just be multiplied out. I'm going to write one more line here, then I'm going to take a second, pause it, and screenshot this for saving. So multiplying the z out and rewriting this one more time, we're going to have x squared plus 1 equals. This I think I'll just leave alone. A times x cubed plus x squared plus 2. This can be just left alone at this point. B times x cubed plus x minus 2x squared minus 2. This might as well be multiplied out now. So this is going to give me a cx to the third minus 9cx plus dx squared. Just slightly running out of room. I'm going to take a moment here and see if I can make myself a little more room for this problem. It's nice how this thing does that. Now I got to get back to my multiplication. Let's see. We did this, minus 9d. I'm going to go back and make sure I know what that is. That was a plus dx squared. It's important that we be able to read these later, so I'm going to take the time here to write that dx squared. Now at this point here, I'm going to pause this and just look this over for problems before I continue on with the video. Folks, I'm back here, and I made a few adjustments here. Make sure that everybody, if anybody's watching this video here, this was a 4, and I think I made a mistake here and turned it into a 9 by accident, but that 4 makes this guy a 4, this guy a 4. My previous work, I think, had 9s there. Also, I'd written a 1 here, but that's supposed to be an x. There was a 2 that I think I forgot, but I believe this line now is good. Now, I'm going to take a moment here and get rid of some things I don't need, and we're going to focus on just this line. So, get rid of all of this. Okay, and now this, we're going to move up here, because the rest of this problem really is about this line now. This line that I've got written here. All right, so now what we have to do is we have to determine the constants A, B, C, and D. And the way we're going to do so is by comparing coefficients. And what I'm going to do here is I'm going to start by comparing the x to the third power coefficient. Now, there is none on the left, but you notice there's one on the right. And because there's one on the right, that means we can write an equation for it. So, because there's no x to the third coefficient, we can say 0 equals. Now I'm going to glance over to the right for anything that has an x to the third. This does, and for the sake of keeping the equation short, I'm just going to do the coefficients. So this is going to be a plus b from this term. Here's another one, plus c and I think that's it. Okay. Now what we're going to do is we're going to compare the x squared terms. So there's one here. We look over to the right. we're going to have one right here, 2a from this product. This one right here is going to be minus 2b from this product plus d for that guy. Next thing, the x terms. There's one x term here. This product is going to give us 1. This product is going to give us 1. This one, minus 4c. I think that's it. And then the constant terms. So we look to the left, there's no constant here. This product is constant. Here's another constant, minus 2b. And there's another constant, minus 4d. So I'm going to take a moment here and double check all these equations before I move on. So folks, we're back. I've double checked the work, and I went back and unexpanded this back to what they were before I multiplied them out. The reason for multiplying them out was to write this system of equations. However, I'm going to, a little bit later in the video, I'm going to talk a little bit about how to use these previous lines to help simplify our system down. So, very important part of this problem is how to write this system of equations. And again, this equation came from comparing the x to the third terms. If I wrote it out with the x to the thirds, it's 0x to the third equals ax to the third plus bx to the third plus cx to the third, and the x to the thirds just cancel. Same thing with the x squared, same thing with the x terms. So where this system of equations come from is the most important part of these problems. If you can't do that part, you're sunk. Okay, the next part is how to solve the system. Now there's a couple different, there's lots of ways of solving systems of equations. This can be solved for just by brute force. We could, use substitution, or we can use tricks like I could multiply this equation by 2, add it to this one to get the b's to cancel, things like that. However, with these long problems, we can also use our previous line to nail down some of these unknowns right away by evaluating the equation at very specific values for x. Remember that this equation has to be true here for all x in our domain. There's no domain restrictions on this other than the what was I going to say here? Actually, it's true everywhere. This equation has to be true for all values of x. And what I can do is if I choose very specific values, it can really make these things fall apart nicely. So here's what I'm going to do here. I'm going to take a look at this system at x equals 2. Now the reason for doing that at x equals 2, as we glance through this line, take a look at this middle term, this x cubed plus x minus 2x squared minus 2. And I've written what it was previously before I multiplied it out. If we evaluate this at x equals 2, this becomes a 0, and this entire term is gone. When I look right here, this x minus 2 here, when we evaluate that at 2, this entire term also gone. So if we take a look at this line and evaluate it at x equals 2, the left-hand side is 2 squared plus 2, coming from x squared plus x, equals a times. Now when we put a 2 into this equation here, it doesn't go away. It equals some constant. This is going to be a 4. And then 2 squared plus 1 is 5. And what we have now is an equation where we can directly find a. This is a 6 over 20. So a is 3/10. Now I'm going to glance this equation over and see if there's any other sneaky value I can use for x. And I notice that sitting right here is this x plus 2. If we evaluate this at x equals -2, this term will go to 0, and this term will go to 0. So if we evaluate that line at x equals -2, -2 squared plus a -2 equals, and again, this entire term is gone because of the x plus 2 evaluated at x equals -2. This term is not gone because -2 minus 2 is not 0. So we're going to have plus b times, when we put a -2 right there and then subtract 2, that's going to become a -4. And then -2 squared is 4 plus 1 is 5. Then we look over here. If we put -2 right here, this term is gone. So this equation is done. So let's see. -2 squared is 4 minus 2 is 2 equals b times -20. So it's looking like b is equal to -1/10. I'm going to take a moment here and pause this and just reflect and think happy thoughts. Okay, folks, I'm back. Looked it over for mistakes. We think it's looking pretty good. I went ahead and screenshotted it. All right, we now have values for a and b. Now I'm going to look over to my equations here, and I see one right here that should allow me to get c. So we got 0 equals a, which is 3/10, plus b, which is -1/10, plus c. So this is going to read 0 equals 2/10, which is 1/5, plus c. So now we have c is -1/5. Last, we need to evaluate d. Oh, either of these look fine. I guess this looks maybe like the simplest. I need a little room here, so I'm going to get rid of some stuff we don't need. Alright, so now I'm going to use this line to try to figure out what d is. So we're going to have 0 equals 2a. I'm looking right here, a is 3/10, so 2a would be 6/10 minus 2b. Now b is -1/5, so this is going to become plus 2/5, and then minus 4d. So we're going to have 4d equals, how about we write this 6/10 plus 4/10. And what I did is I took this minus 4d, put it to the left, wrote that as 4/10. Now these add to 10/10, which is 1. And when we divide by 4, we get d equals 1/4. So we have all the constants we need. I'm going to kind of write these off to the right. A is 3/10, B is -1/10, C is -1/5, D is 1/4. So we now have everything we need to do to go back and rewrite our integrand here as the sum of 4 different fractions. So I'm going to take a moment here and screenshot this again. Or just save copy. Boom. Get rid of a bunch of stuff I don't need. Okay. So now, remember what we were trying to do. We're trying to evaluate this integral. So remember that we took this and we wrote it, ooh, I don't have it here, but it was a 3/10 over, and it was either the x minus 2 or the x plus 2, and I'm going to ask my crew here, which one was it? Otherwise I'm going to have to go back. Was that plus or minus 2 over a? It was -2 first. Okay, thanks. Dx plus, the next one should have been the b over x plus 2. The next one was cx plus d over x squared plus 1. So what I've done now is just taken this and wrote it a over x minus 2 plus b over x plus 2 plus cx plus d over x squared plus 2, and then divided it up into 3 integrals. Okay, so this guy, constants can come out in front. And we'll deal with that in a minute. Same thing here. Constants can come out in front. This one can be divided into 2 more integrals. One of them is going to be minus 1/5 integral x dx over x squared plus 1. Need a little room. Don't need these anymore. And then the last integral here is going to be 1/4 integral 1 over x squared plus 1 dx. Now, for anybody watching, I would point out that really no calculus has been done at this point. All we've done is all the algebra required to take this big mess and break it into the sum of these smaller messes. Problems like this will really make people appreciate the numerical methods. All right, now these have to all be integrated term by term. I'm going to start doing that. So the first one integrates to natural log of x minus 2 plus a constant. I'll tack the constant on at the end. The next one integrates to natural log of x plus 2. The next one, now notice, I'm going to try to do this reasonably quickly. Notice that if u were equal to x squared, du would be 2x dx. So what I'm going to do is put a 2 here and a 2 down here. This is now of the form integral du over u, which is natural log u. This 2 and the 5, that's going to make that a 10. One-fourth integral 1 over x squared plus 1. All right, so that one I can't do in my head. This one reminds me of Pythagorean theorem, which means we have a trig sub coming. So what I'm going to do here is I'm going to take a moment, pause this, screenshot it, get rid of what I don't need, and focus on that very last integral. Okay, folks, I'm back. Gotten this thing written out, or gotten rid of stuff I don't need. At this point right here, I've moved this line up here. I should actually tack a constant on there. I'm just going to call that C1. The reason is because we got a bunch of integrals that have done. Each one has introduced a constant. Suffice to say, you could add up all those constants. They add to some other constant that I've called C1. Now we need to work on this integral dx over x squared plus 1. Now, to me, that's a Pythagorean theorem looking thing, which means trigonometric substitution probably would be a good way to hit that. I always start by writing out sine squared plus cosine squared equals 1. It helps me choose what to use for the subs. If we take this and divide it by cosine squared, this is going to read tan squared plus 1 equals secant squared. Now I notice tan squared plus 1, x squared plus 1, so the substitution that I believe that will help here is going to be let x equal tan theta. If we do, then dx is equal to secant squared theta d theta. Which means we can rewrite this integral. Integral secant squared theta d theta over. Now this is now going to be tan squared plus 1, which I believe I erased it, but I think that was secant squared. secant squared theta. At this point, something nice in this problem finally happens here. So this ends up being the integral of d theta, which is theta, which we get from here, which is the inverse tangent, of x plus a constant. So finally we got to the end here. We can write out our original integral equals, so I'll try to get this answer written out in one line. 3/10 times the natural log of x minus 2 in absolute value, because that thing needs to be positive, minus 1/10 times the natural log of x plus 2, again absolute valued, same reason, minus 1/10, here the x squared plus natural log of x squared plus 1, I'm going to go ahead and just put that in soft brackets and deliberately avoid the absolute value because it's not needed, because x squared plus 1 is positive definite for all values of x. If you put absolute values there, it's not incorrect, but there you can leave them off. Plus 1/4 the inverse tangent of x plus some other constant, which I'm going to call C happy face, because I'm finally done with this integral. So I'm going to go ahead and pause this, or actually I got to stop it. I hope that this video helps demonstrate how to apply these techniques. And for those of you who have me where we talk about numerical integration, I think that this example is a good one to show why numerical integration is should be very well appreciated. So anyway, have a great day.